Look at a modern rocket sitting on a launch pad at Cape Canaveral. What you are actually looking at is a giant, floating gas tank where 96% of the total weight is just the fuel needed to move the rocket itself. Think about that. If you bought a car and 96% of its total weight had to be gasoline just to pull it out of your driveway, you would call it a manufacturing disaster. In aerospace engineering, we call it the rocket equation. For the last 100 years, humanity has been trapped by a brutal, unforgiving law of physics. To carry more payload, you need more fuel, which requires a bigger rocket, which requires even more fuel. This is exactly why we haven't set foot on the moon in over 50 years, and it is why sending humans to Mars using our current propulsion methods is a statistical nightmare. Chemical rocketry has officially hit its structural limit. We are effectively stranded in Earth's backyard. But behind closed doors at NASA, DARPA, and private labs, a massive paradigm shift is happening. Engineers are developing radical alternatives that bypass the rocket equation entirely. From orbital elevators to laser-driven sails, the age of combustion is ending. Here is the exact technology that will finally break us out of the cradle. To understand where we are going, you have to understand why current tech cannot get us there. Chemical rockets generate massive raw power, what engineers call thrust. It is exactly what you need to punch through Earth's thick atmosphere in an intense 8-minute sprint. But they have terrible specific impulse, which is just aerospace speak for fuel economy. A standard chemical engine maxes out at a specific impulse of about 500 seconds. It burns through hundreds of thousands of gallons in minutes, leaving virtually nothing left for deep space travel. It is a lightning-fast sports car with a gas tank the size of a thimble. We do have an alternative in operation right now: electric ion propulsion. Spacecraft like SpaceX's Starlink satellites and deep space probes use these. Instead of igniting chemical explosions, ion thrusters use electric or magnetic fields to accelerate noble gases like xenon or krypton up to an astonishing 140,000 kilometers per hour. Because these particles exit the engine at extreme velocities, the fuel economy is 10 times better than a chemical rocket. It is the ultimate marathon runner. But it has a fatal flaw. The raw thrust is practically non-existent. An ion thruster generates roughly the same amount of physical force as the weight of a single sheet of printer paper resting on your hand. If you turn an ion engine on while it is sitting on Earth, absolutely nothing happens. It cannot fight gravity, it cannot fight friction, and it takes days of continuous operation in space just to accelerate a spacecraft to highway speeds. While it is perfect for micro-adjustments on small satellites, it is completely useless for moving massive payloads, heavy machinery, or human crews across the solar system. So how do we bridge the gap between massive chemical thrust and efficient electric speed? The answer NASA is betting on is nuclear. Right now, NASA and DARPA are actively developing nuclear thermal propulsion through programs like DRACO. The concept is incredibly elegant. Instead of burning chemical fuels, you place a high-assay low-enriched uranium fission reactor inside the rocket. You pump a liquid propellant, like liquid hydrogen, directly through the roaring nuclear core. The intense heat instantly vaporizes the liquid into a superheated, rapidly expanding gas, which is violently jettisoned out of the nozzle. This gives you the best of both worlds. You get the high, immediate thrust of a traditional chemical rocket, but with double the fuel efficiency. A nuclear thermal rocket cuts the transit time to Mars down from 9 agonizing months to just a few weeks. This isn't just about saving time, it's about human survival. Deep space is filled with lethal cosmic radiation. Every single week astronauts spend floating between planets fills up their lifetime radiation allowance. By doubling our speed, nuclear engines solve the health crisis of deep space travel before we even arrive. If we want to go even faster, we turn to nuclear electric propulsion. This involves putting a literal nuclear power plant on a spacecraft to generate massive amounts of continuous electricity. Instead of relying on weak solar panels that lose efficiency the further they get from the sun, a nuclear reactor can supercharge a massive array of heavy-duty ion thrusters. This allows a spacecraft to accelerate continuously for months on end, reaching top speeds that chemical rockets could never dream of achieving. But what if the real solution to the rocket equation is to stop carrying fuel altogether? This brings us to propellantless propulsion, and the most mature concept we have is the solar sail. Photons, particles of light streaming from the sun, do not have mass, but they do have momentum. When millions of photons strike a highly reflective, ultra-thin material, they transfer that momentum, giving the sail a tiny, continuous push. NASA has already successfully deployed its advanced composite solar sail system in orbit, monitoring how a massive square sheet can maneuver using nothing but sunlight. The beauty of a solar sail is that it requires zero onboard fuel. As long as the sun is shining, the spacecraft is accelerating, while the initial push is incredibly gentle. Over months and years of constant, uninterrupted solar pressure, a solar sail-propelled craft can reach speeds that completely eclipse standard rockets. Future designs call for sails larger than football fields, allowing uncrewed cargo probes to navigate the solar system for a fraction of the cost of traditional missions. But even solar sails have a boundary. Once you cross past Jupiter, the sunlight fades, and your acceleration drops to zero. If we want to reach the outer edge of our solar system, or travel to the nearest star system, Proxima Centauri, we need a power source that doesn't fade. We need directed energy propulsion. Imagine building a massive, kilometer-wide laser array either on Earth or in permanent orbit. Instead of relying on the faint light of the sun, we aim this high-powered laser beam directly at a spacecraft equipped with a specialized sail. By focusing a concentrated stream of energy across vast distances, we can accelerate a probe up to a staggering 10% the speed of light. At that speed, a trip to Mars takes just a few days, and a journey to Proxima Centauri, which would take a standard electric thruster 81,000 years to reach, could be completed in just 40 years. It turns interstellar travel from a multi-generational fantasy into something a single human being could witness within their lifetime. The challenges here are no longer theoretical physics, they are engineering problems. We have to figure out how to keep a laser perfectly aimed at a tiny target millions of miles away without the beam spreading out, and how to prevent the intense energy from melting the spacecraft's sail. These are difficult, expensive problems, but they are entirely solvable if the funding is there. Finally, we have to look at the ultimate infrastructure project that could end the rocket equation on Earth forever, the space elevator. Instead of building more complex rockets to fight gravity, companies like the Obayashi Corporation are actively designing a 96,000-kilometer cable made of advanced carbon nanotubes. One end is anchored to a spaceport on Earth's equator, while the other end extends out into deep space, attached to a massive 12,000-ton counterweight in geostationary orbit. Once the cable is secure, we can use mechanical climbers powered entirely by electricity to lift payloads, satellites, and space station components directly into orbit. It completely eliminates the need for explosive launches, lowering the cost of putting mass into space by over 90%. Humanity is currently standing at the exact same crossroads our ancestors stood at a century ago. The era of sitting on top of controlled chemical explosions just to reach orbit is reaching its natural conclusion. Whether it is through the raw power of nuclear reactors, the endless acceleration of solar sails, or laser beams pushing us toward the speed of light, the technology to colonize our solar system is already leaving the pages of science fiction. We are about to break the limits of the rocket equation, and once we do, the stars will no longer be something we just look up at, they will be a destination.